systems of inequalities. So we have systems of inequalities as well as systems of equations or equalities. Okay, we've been working with the systems of equations where we've been solving them graphically and two forms of algebraically, either by substitution or by elimination. So now let's talk about our systems of inequalities. For the most part, we will solve them graphically, okay, because there's going to be multiple solutions to a system of inequalities, just like we would have when we solve a regular inequality with one variable. There's infinite solutions. Well, the same thing holds true with a system. So it says we have to find all points that make the inequalities true. So it says consider this system here and determine if 3, 8, and 5, 9 are solutions to those systems. So we do the same thing to verify. So we would say, is 3 plus 8 greater than 10? And that's true. And then 8 is greater than or equal to 3 times 3 minus 5, which is also true. Okay. So this is a solution to that system. So our second one, 5, 9, we do the same thing. Plug that into the original system and see if we get two true inequalities. Because remember, this is a system and it's an and situation. So both have to be true in order for it to be a solution. So is 5 plus 9 greater than 10? And that is certainly true. And 9 is greater than or equal to 3 times 5 minus 5. And that is false. So we end up with that 5, 9 is not a solution to our system of inequality. So let's take a look at graphing. So it says graph the solution set. Now remember, because this is a system of inequalities, we have infinite solutions. So we're talking about a solution set here. It's not just going to be one point that's going to make this system true. So let's take that first one and solve it for y. Then we're going to go to our calculator. And the second one is already solved for y for us. So let's take a minute and type those two in to your calculator and see what they look like. So because we have the inequality, obviously our calculator graphing portion comes up with an equation. So if you just hit the delete key, it will bring up the inequality symbols that we need to use. So that first one was negative x plus 10. Oops. I got a greater than. There we go. Negative x plus 10, hit enter. Okay. Notice that the shading occurs for us, and if you click on that line, it will then change it to a dotted line because that greater than symbol indicates that it's not equal to on the line, but all the solutions are above the line. So hit Control G to type in that second inequality, and our second one is, what are we looking at? 3x minus 5. And it's greater than or equal to. So delete, greater than or equal to 3x minus 5. So now when I hit enter, okay, I can't see where those two are true. I can see where the second one is true. I can see where the first one is true. But we've got to be able to see where they're both true, because that's going to be the solution. So a couple different ways. You can change this. We double click on that upper y value. I don't know, you can make it 15, you can make it anything you want, just so you can see a little bit more of that graph. Okay. All right, so now you can produce that on your paper here, or we can just go to that next one. I think you guys are fine with graphing that because we've done them not as solutions, just as your single inequalities. Okay? So make sure that you're labeling. Now, the calculator obviously has that limitation. It just kind of puts the label wherever. Your label should indicate where the solution is, because that's what you're labeling. You're labeling the solution. So anytime you label an inequality, it's got to appear on the shaded side. Now, the solution to this system is where this darker shading occurs, okay, where both of them are true. So if we look back, does that original point, okay, that came out to be true, 3, 8, is that in that dark shaded region? So 3, and then if we go up 8, it certainly is. Oops. All right, so let's look at number 2. It says, on the grid below, graph the solution to the system of inequalities shown. State a point that lies in the solution and one that doesn't. So let's do this one by hand. So we know that the slope is -3/2, and the y-intercept is 2. Now this one, okay, that x is greater than or equal to -2, that's going to be that vertical line. It's only got an x-intercept. It doesn't have a y-intercept. So starting off with the first one, we're going to go up on our y-axis 2, and then we're going to go down 3 and right 2. And our inequality symbol is less than, so we've got a dotted line there, because it's not equal to. Okay, use a straight edge to make sure that your solutions are as accurate as they can be. And then remember, there's that infinite amount of solutions to this, so where are all the y values less than? Okay, are the y values less than above the line? Do the y values that are less than go up, or do the y values that are less than go down? Those y values that are less than are all going to go down. And make sure that you label it on the shaded side. So y is less than -3/2 x plus 2. The second one, x is greater than or equal to -2. We just got an x-intercept, okay? So now we talk about that vertical line, right? It has an x-intercept, and the slope is undefined, or no slope. So let's find where x is -2, and it is greater than or equal to, so we're going to include those points all along that line, so we're going to use a solid line. And where are all of our x values greater than -2? Greater than is going to go to the right. So all of those solutions that are greater than are going to go to the right. So now, where are all the solutions to this system? Remember, it's got where both of them are true. So your solutions are going to occur right there where that shading overlaps. And let's just back up and make sure that we label the solution set for that second one that we graphed. X is greater than or equal to -2. And now it's saying pick a point that is in the solution set. Pick a point that's in the solution set. So obviously there's a variety of answers that are going to make this true. I might go with something pretty easy. Right there in the center at 0, 0. That's a point in the solution set. And then a point not in the solution set is any point that doesn't fall in that double shaded region. So we could pick a point that is just in that x is greater than or equal to -2 solution. You could pick a point that's not in either one of those, which you can't really see that on this graph. Be someplace up in here if we were to extend. So let's see, I'm just going to pick that initial one that I initially plotted. 1, 2, 3, 4. 4, 3 is not going to be in our solution. Go ahead and flip the page, and I think we're going to hop over question 3, and let's take a look at question 4. So question 4 is still a system. Now remember, what makes something a system, it's got 2 or more equations or inequalities. So this one has 3. So it's still an and situation. So everything has to be true in order for it to be a solution. So it says determine which, if any, of these points is a solution to the system. So you've got to go through that process of plugging in each one into all 3 of those inequalities. So is 4 greater than or equal to -2? That's true. Is -1 less than 4? That's true. So far, so good. And now is 4 less than or equal to 2 times -1? 4 less than or equal to -2? Well, that's false, so that's not going to be a solution to the system. Same thing with 3(1). Is 1 greater than or equal to -2? That's true. Is 3 less than 4? That's true. And now let's see if it makes that third one true. Is 1 less than or equal to 2 times 3? And that is absolutely true. So 3(1) is in the solution set. Part B asks us to sketch the solution to the system on the grid. So again, let's do this one by hand. It should be pretty easy. Y is greater than or equal to -2. So that's just got a y-intercept. So that's going to be our horizontal line. And it's equal to, so we've got a solid line there. Here's y -2. And then shading that, y is greater than -2. It's going to be all those points above the line. And second one, x is less than 4. So it's just got an x-intercept at 4. And that's a dotted line. X less than 4, so we're going to go to the left. And make sure that when you're shading, you're not scribbling those lines pretty neat, because obviously once we get more than 2 on there, it could get a little messy. And then finally that third one, okay, we've got a slope of 2 and a y-intercept of 0. Okay, so it starts right at the origin. And we're going to go up to right 1, or down to left 1. And it's going to be another solid line. Again, you're looking for that accuracy. Use your straight edge. Okay, don't freehand those lines. Our shading for that one, y is less than, so that's going to go below that line that we just graphed. And where do the solutions fall? The solutions should fall right where all 3 of those shadings overlap, and we should start to see that occur right in that triangle. Part C says, find the area of the portion in the xy plane that represents the solution. So I mentioned that that does give us a triangle. Hopefully you can see that. Highlight that. So the area formula for a triangle, 1/2 base times height. So 1/2 the base of that triangle, 1, 2, 3, 5, 5. And then the height of it, 3, 4, 5, 6, 7, 8, 9, 10. The area of that triangle 5 units squared. We don't know what the units are, so we're just going to put units squared. And it says, why does the dashed line on one of the borders not make a difference in terms of the area? Think about what area means, okay? So does this dotted line right there make a difference to the area? And the area is that space inside, so it doesn't matter whether we include that dotted line or not. Okay, you're just talking about the space inside. Okay, so it doesn't make a difference. Because area is the space inside. Alright, go ahead and flip it. Let's go to that next lesson and let's take a look at that first question. Right? So there's many situations that arise in business or engineering that necessitate systems of linear inequality. So this is the stuff that we did in the first lesson is just exercise for your brain. This is that application of it, stuff that really makes sense. So it says the region in the XY plane that solves the system often represents all the viable solutions, all of the possible solutions to the system. And giving ourselves a visual is going to be helpful. So let's look at this model. It says that John mows yards for his father's landscaping business for $10 per hour. Okay, so that's mowing lawns. And he also works at a bakery at $15 per hour. He can work at most 52 hours during the week in the summer, and he needs to make at least, so we've got some keywords there, $600 per week to cover his living expenses. So it says if John works 14 hours mowing the lawn and 30 hours at the bakery, does that satisfy all the problem's constraints? Now the constraints are that he can't work more than 52 hours, that's a constraint to his lifestyle, and that he does need to make $600 a week because he needs to obviously have a roof over his head and put some food in his mouth. So does that situation satisfy what he needs? So if we're talking 14 hours times $10 an hour mowing lawn, plus we've got 30 hours at the bakery at $15 per hour, does that give us $600 or more? And that, if you do that calculation, that's $590. So that's not going to work for him. So that situation is not a viable solution for what he needs. Part B says, if X represents the hours John spends mowing lawn, and Y is the time that he's at the bakery, write a system of inequalities that describes the scenario. So we've got two situations here. We've got the hours that he works and then the money that he makes. So if we say the hours mowing lawn plus the hours at the bakery, that has to be less than or equal to 52 hours. Because remember, it says he can work at most 52 hours in the summer. Now the second situation is the money that he makes. So he makes $10 for every hour mowing lawns plus $15 for every hour at the bakery, and that amount has to be at least $600. So he can make $600 and just make it, or he can make more than that and have a little extra. Okay, so that's going to be that greater than or equal to $600. So we have an hours inequality, and then we have that money to make up the system. It says if John must work a minimum of 10 hours for his father, minimum of 10 hours for his father, will he be able to make enough money to cover his living expenses? So 10 hours at $10 an hour. So that would leave, he could work potentially 42 hours at the bakery at $15 an hour, and that gives us, if you do all that calculation, he ends up with $730. So yes, that would work for him. Now it says graph the system of inequalities with the help of your calculator and use the space below. Okay, so let's go and let's take that system that we've got. Now in order to graph it, obviously we've got to get y by itself in both inequalities. So the first one's going to be y is less than or equal to negative x plus 52. And the second one is going to be y is greater than or equal to negative 2/3 x plus 40. So let's go ahead and go to the calculator and graph those two. So you want to clear out, you want to get a new graph in there, don't save anything. And the first one is going to be a less than or equal to negative x plus 52. Okay. Wow, that looks kind of crazy. Okay, we're going to do something with the graph in just a minute. So now let's hit Control G and let's type in that second one, and that's going to be a greater than or equal to. So that's negative 2/3. X plus 40. And hit enter. Okay, so everything seems to be shaded in here. Okay, but let's think about the context of this problem. We're talking about money in hours. Okay, two situations that we're not concerned with negative. So what we need to be looking at is we just want that first quadrant. So if we go to, we can do it a couple different ways. We can change this to 0. We can change that high point, and our y-intercept is 52 for that first inequality. So I don't know, I'd make that maybe a 60. Okay, and now we're starting to see something here. And we can make this, I don't know, try 25. Maybe even make that a little bit larger, 30. We can move those labels out of the way. Grab that one. Just so we can maybe try even 50 on that. There we go. Okay, so you've got to think about the context of the problem and what you're looking at when you go to graph this. Okay, so right here in the middle, okay, that's less than 52 hours a week, or 52 or less, and then it's greater than or equal to $600 so he can live. So all of this in here in that dark shaded region is going to fulfill both situations for him. For the sake of time, I'm not going to reproduce that on the graph. So let's take a look at 2 more questions and then we'll be done. Okay, it says John's father needs him to work a lot at the landscaping business. Show the point on the graph that corresponds to the greatest number of hours that he can work while still covering his expenses. Okay, so when I go back to my calculator, that point right where those two intersect, okay, is going to be that situation. Okay, right there on our graph. Okay. So what is that? Okay, this is the intersection point. Graph. And then it says, algebraically find the greatest number of hours that John can work for his father and still cover his expenses. I explained how you found your answer. Okay, so solving this algebraically, we're going to set those two equal to each other. Okay, we talked about it graphically. It's that intersection point. Well, that's where those two equal each other. So we're going to take and make this an equation. Okay. solve it for x. Okay, so going through and combining like terms, we are going to end up with getting x all by itself. We're going to get 36 hours. We'll do another question tomorrow on the back side here, as we'll do number 3, okay, as a warm-up. If you want to take number 3 and work through it so you can come in prepared, that'd be great. I will start with number 3.